I guess it's recording. Okay. So let's just assume it's recording. It looks like it is anyway. Sure, why not? Okay. So I guess we're recording. And let's fix our camera. And let's turn some things on here. So is it just the three of us today then, I guess? We can live with that, I suppose. Now, were you all able to get to the videos that I posted last week? Anybody struggle with, what's that? You couldn't find them? I sent you the link in an email through WebAssign. And let's see if the emails through WebAssign should go to your whatever email you have entered in WebAssign. Should go to that email address. I put an announcement up as well. And that should have showed up in your WebAssign page. What's going on here? Now I was kind of tracking progress on homework and it looked like you guys were doing okay. Is that not the case? Are there any assignments that you would need some extra time on or anything? I got that email. And we can sit down and figure that out together. Anything else? Okay. That's what we like to hear. And let me see if that announcement actually got posted. Let me take a look here real quick. Okay. Okay. And that is the same place where any video from this class will be posted. It's just a playlist on YouTube. And I'll just post all my videos there, including this one today. So, homework from Thursday would be, how come I don't have anything going on here with my, alright, I'll fix that. Just a second. Let me take a look at what's going on here with my... I don't know what's going on with my screen here. Why it's not showing anything. That's not helping. There we go. Okay. Alright, so let's take a look at some of this stuff here and see if we can figure out. So today's homework due today is at the wrong time. Let's fix that first. That was 6 point... What is today, the 1st? Yeah. So just one of them is wrong. We'll fix that really quick. Here. p.m. Okay. Okay, that's fixed now. And then we're supposed to start off with chapter 7 today. We might get through the first section of chapter 7 today after we've finished fixing everything from last week and catching everything up. So was it homework 6.5 that you had questions about? Is that correct? 6.2 and 6.4. Okay. So let's go look at 6.2 and 6.4. So let's edit those schedules so that they can be due. If we talk about them today, do you think that it'll be all right? Do you think you'll be able to get them done by today, or should I make them due tomorrow? What? Okay. Any idea? Should we make them due today and then we'll see? We'll make them due today and see what happens. Okay, so 6.2. No, that's the wrong one, dang it. Let's move to week 4. 5. There we go. Do that, there we go. That's better. Okay, so I've moved those. Now the other thing that we have to take a look at is the end of this week, because we're supposed to start chapter 7 today, and then we would continue through chapter 7 Tuesday and Wednesday, but then we have exam 6 that's supposedly going to be due Friday because I forgot about the 4th of July. And so, wait, what's going on here? Okay. So anyway, we won't be meeting either Thursday or Friday this week, right? So what we need to do is we need to say this is Monday's assignment. These are Mondays. This is Tuesdays. Almost 7.6 will cover Wednesday, but we want it to be due next week. So let's put this next week on Monday. Oops. Reschedule to week 6 on Monday, July 8th. Schedule that. And then also we will put in this one here. Schedule week 6 on Monday, July 8th. Schedule. And then we also want to put the test next week. Now, will you be able to finish the test by next Tuesday evening? Okay, we'll put it due next Tuesday evening at 5 p.m. if that'll work. And then you can just take it whenever it works for you. Tuesday, 5 p.m. Okay, and then I'll have some more scheduling to do here next week, but we'll take care of that next week. What was your question? Firstly, I wouldn't be too nervous about it. I generally don't do study guides because the homework is the study guide, and you guys have been doing well on the homework. I honestly wouldn't be too nervous. I think I can tell you how many questions are on the test, and I can tell you what kinds of questions are on the test. But I generally do not give out study guides. And the reason that I say don't be too nervous is because there isn't anything that we've done in this class so far that you haven't been doing in every homework assignment. It's not like we learned something in chapter 1 and chapter 2 that we're not still using, right? So this is stuff that is extremely comprehensive all the time. So if you're still getting through homework assignments pretty well, I wouldn't worry too much about it. Also, the test is open book. So it is an open book test, so as long as you know where things are in the book, I wouldn't worry too much about forgetting things or not being sure how to figure things out. I think you guys are all very well equipped for this test. So with the test, you can have your book. You can even use your own computer if you prefer to do that. That's fine with me. But I don't want you to use your homework notes. I don't want you to just copy out of your notes. And generally what I do is about half the questions on the test are, let's see, I think there's 10, maybe a few more than 10 questions on the test. I can't remember exactly what there are, but let's take a look. Let's see, the test is... Okay, exam 1 through 6, here it is. So it looks like we've got 10 questions on the test, and it looks like 1, 2, 3, 4 of them are kind of multi-part questions where there's more than one thing that you have to answer, so there's some calculating there. There's going to be about 3 questions that are probably shorter calculation questions. So maybe 6 or 7 questions that are calculate the answer kind of questions. Some of them shorter ones, some of them a little bit longer, but none of them are very long. And then the rest of them, the balance of them, probably 3 or 4 questions are multiple choice or short answer type questions from the conceptual questions and multiple choice questions. So that's kind of the basic idea of it. 10 total questions and a total of 14 points. On the exams, you will have 3 opportunities to get answers correct instead of 7. So you still have, the chance to go back and fix something if you get it wrong. On the exams, however, I don't give you all of the learning tools that I give you on the homework. So it's not necessarily as convenient to find things, but if you know where things are, you should be able to do it. Any other questions about the exam? All right. Generally, this first exam is not, most students are pretty nervous about it, but usually the students come out okay, so I'm not too worried about you. Let's take a look at this homework 6.2 and see if we can't answer your questions that you might have here. So homework 6.2, we have, looks like 4 questions. Was there any particular problem that you wanted me to look at, or do you want me to just look at all of them? Okay. So you're close, but not quite there. Okay. Well, if this is section 6.2, so let's go take a look at the book really quick and see what we're learning in 6.2. Make sure we teach you the right things here. I have a tendency to skip ahead sometimes, and I'm not sure exactly where I am in the book. So in 6.2, slowly my book will open here, hopefully. So this chapter, in general, we're dealing with momentum and collisions. Excuse me. But in particular, in 6.1 and 6.2, they introduce us to momentum and impulse, and momentum being mass times velocity, and that is different than kinetic energy, right? Kinetic energy is another thing that is conserved in certain situations, but it's calculated differently. And it seems kind of weird that you would have two things that are almost the same but different. But it's just what they observed. They just observed that these two quantities just had this tendency to be conserved, and so they went with it and discovered all these things. But you also notice that the momentum is different than the kinetic energy in that it is a vector quantity, that it has direction. Momentum cares about which direction it's going, because it is mass times the velocity vector right here in this equation. So, impulse being a force times a time is also related to the momentum. Momentum is caused by an impulse. You can actually give momentum to another object by applying a force over a certain amount of time. And you have this impulse momentum theorem, where the amount of impulse that is imparted to an object is equal to the change in momentum of the object. So you apply a force over a given time, and this is a net force. So if it's a net force, meaning there's no other forces that are canceling out, like friction or anything else, then that object is going to change its momentum. It's going to go from some initial velocity to some final velocity, and that change in momentum will be equal to the force times the time that force is applied. Then they talked about the momentum being the impulse being the area under a curve in the force time graph and everything else. And again, here we learned that boxing is one of those areas where this kind of illustrates itself. Another reason that boxers kind of roll with the punches is that it lowers the amount of force being applied to their head, and at the same time it increases the amount of time that the force is applied to their head, but the force is so much smaller that the impulse ends up being much smaller. So, in example 6.1, they're going into calculating momentum of an object, the impulse of a golf club on a golf ball, and so on and so forth. And then we get into 6.2. Let's go to 6.2 really quick. We're done with impulse and momentum here. Let's go to 6.2. Where is 6.2? Somewhere along here. Here we go. And 6.2 is conservation of momentum. Now, we said before that energy is not always really conserved. Kinetic energy is not always conserved, for example. It's sometimes changed into another type of energy, and so the energy goes back and forth, or it gets lost in a type of energy that's irrecoverable, like heat, friction, sound, other things like that, where it just dissipates and kind of leaks out into the universe somewhere. But momentum is always conserved, it turns out. And there's always a way to kind of account for where it went. And so they introduce us to the idea of collisions. In a collision between two objects, the momentum of the objects before the collision, if you add up all the momentum vectors from the objects before the collision, then add up all the momentum vectors after the collision, the total momentum before will equal the total momentum after. And so what we've got to do is we kind of think about what that implies, what that means to us, since we know something about vectors. So I'm going to switch over to my little whiteboard here. And we'll take a look at this idea. So, first of all, let's imagine that we have a car, or let's just say we have a ball. This is going to be ball A. This will be ball B, right? They have different masses. This one has little mass m, this one has big mass m. And this one has some velocity that's going this way, it's not that big, and this one has a much bigger velocity going this way, it's bigger. We'll just say it that way for simplicity. And they're going to collide, they're going to hit each other. This one has a momentum of A, and it's going to be a vector. It's going to equal the little mass times the little velocity. And this one has momentum B, which is going to be the big mass times big velocity, and those are vectors. Momentum A is pointing to the right, and it's not a very big arrow, so I can represent it with this arrow. And momentum B is pointing to the left, and it's a much bigger arrow, it's pointing this way. And so if you wanted to add these two together, you're going to get an overall initial velocity that is total velocity, P total, equals, or momentum total equals momentum A plus momentum B, right? And momentum A being this little arrow pointing to the right, plus momentum B being this big arrow pointing to the left, is going to equal an overall kind of smallish, mediumish vector pointing to the left. So our total momentum for this system is pointing to the left, and it's whatever value it is, because we added that together. Now after the collision, A and B will have different velocities. In fact, A might have a much bigger velocity, and B might actually be going the same direction, just with a smaller velocity than it had before. Because that's what often happens with really big, with collisions with big items and small items, that the small item bounces off and goes flying away, and then the bigger item just slows down. It doesn't necessarily stop. We saw that example before. And so maybe that's what we do. And in the end, if we add these two momentums, so this is momentum A, this is momentum B final now, and momentum A final now. If we add these two together to get our total momentum, you can see that we still get a total momentum that is kind of small, medium-ish to the left. And in reality, it should be exactly equal to the one that we started with before the problem. And that is the basic idea that we're dealing with here, except that in some situations, we're going to have conservation of momentum with two objects that are separate. In some situations, we're going to have conservation of momentum where two objects stick together, so before the problem they're separate, but after the problem they're actually one item. And then we're also going to have some situations where we have conservation of momentum and conservation of kinetic energy in the same situation. So we need to sort out what situation we're dealing with and figure out how to work it out. So let's take a look. So, conservation of momentum and collisions. We have some examples of collisions over here. First of all, we have these spherical objects that are going to just bounce off of each other, right? Mass 1 and mass 2. Mass 1 is feeling a force from mass 2 on it, force 2 on 1. Mass 2 is feeling a force on it, force of 1 on 2. And they're going to bounce away from each other because of that bouncing force. They've already come racing towards each other, now they're bouncing off each other and bouncing back. And they're bouncing right on axis so that they bounce straight away from each other. They don't glance off of each other. And if this collision between these two masses doesn't lose any energy in any weird way, like the balls don't bend or stretch or deform in some way, or they don't stick together, if they bounce off perfectly off of each other, which is what we call an elastic collision, then the momentum will be conserved, which of course the momentum is always conserved, but also the kinetic energy will be conserved. And this is what we call, I think they call this a contact collision, where the collision actually results in a contact between two objects. But you can also have other situations, for example, in electrodynamics, when you have maybe a positive charge, a positive proton, for example, which is what this is, a positive proton, and a positive helium nucleus, which is two protons and two neutrons, and they come near each other, but they never actually hit. This is a field collision, or it's essentially just a repulsion of objects that are of like charge, right? But it's still considered a collision. And if these two bounce off of each other without losing any energy in some weird way, then they too will have an elastic collision. So what is an elastic collision? An elastic collision is a collision where all of the momentum is conserved, but also all of the kinetic energy is conserved. So from that situation, we should be able to make some equations. And we will. Let's take a look at this active figure really quick and see if we can learn something with it. So here we just have two different balls of different initial velocities. And we can go ahead and make them go different directions. This one going, so now we have the ball on the left going at 10 meters per second, the ball on the right not moving at all. We started off, we can see that all that momentum is going to be transferred into the other ball. Okay. And we can have them moving towards each other and see what happens. So they bounce off and they have different speeds after than when they started. And then you have the glancing collision or the field collision where they just come near each other, and then the forces from the electric fields actually repel each other. And you can change speeds and see how these things affect what's going on, and we see how they do these different paths. So basic collisions. Now let's move on to some more details. What happens if we change the mass? So we change the mass of ball 1, make it much bigger than the mass of ball 2. And then let's say that the ball 2 is going to be going kind of slow and ball 1 is going kind of fast. What's going to happen? Well, see, they come in towards each other and that little ball just takes off and the big ball just kind of slows down a little bit, just like we were talking about earlier. And you can do all kinds of things with this. You can make the mass of ball 1 super big, or make the mass of ball 1 super small, make the mass of ball 2 super big, and start them and see what happens. Just the opposite happens, right? And we can make the initial velocity of ball 1 so much faster, and the initial velocity of ball 2 pretty slow, but going the same direction, right? So you can do all kinds of things with this, is the point. You can play around with it. In the end, there are two things conserved, and it really comes from the impulse momentum theorem that the momentum is conserved. In the end, we say that the impulse on the one object is equal to the impulse on the other object because of Newton's third law, because the forces have to be equal and the time that they're in contact has to be equal. So Newton's third law essentially sets up this system where we have the force of 2 on 1 equals the force on 1 on 2, and that's difference of momentums because that's impulse. And then we just put all the initial momentums on one side, the final momentums on the other, and we get what we call the conservation of momentum equation. Mass 1 times velocity 1 initial plus mass 2 times velocity 2 initial, let me zoom in here, equals mass 1 times velocity 1 final plus mass 2 times velocity 2 final. And so what we've discovered here is that these quantities, these momentums, when you add them together at the beginning, have to equal the same thing as when you add them together at the end. Even though the individual momentums will change, the total sum of them will not. Here they actually show a function, two functions of force versus time for two different objects. So we have two colliding particles, and one of them feels a force that peaks out right here in the positive force direction, and it goes for this certain amount of time. And the other one will feel an exactly the same magnitude of force, just in the opposite direction, so it peaks out in the negative direction for the same amount of time in the same shape, and that is the conservation of momentum. It's interesting that they talk about a squid, how a squid uses this process to move. And I want to illustrate this on my whiteboard again. So let's take a look here. So what happens when you have a squid? Let's see if I can draw a squid. I might get my whiteboard up here on the screen. There we go. So I can draw a squid here, kind of, with his little tentacles. That's not bad. It's been a while since I've seen 20,000 Leagues Under the Sea, but I guess I still know what a squid looks like. Anyway, the squid has this fluid inside of him, I'm going to just kind of color it dark so that we can see the difference between the squid and the fluid maybe. And that fluid is inside kind of a muscle sac. And while the squid is just sitting here, it's just sitting in the sea, the overall momentum, so let's say that the momentum of the squid, P of the squid, is equal to the P of the momentum of its body plus the momentum of the fluid, so P of F. So, and since its body is not moving and the fluid is not moving when it's just sitting still, then the total momentum at the beginning is zero. Right? It's not going anywhere, it's just zero momentum. Well, once the squid decides it wants to go somewhere, it uses this fluid to make itself go forward. How? Well, it squirts the fluid backward. So when it squirts the fluid out, we have this fluid that's in the ocean now, and it's moving backward with a particular speed. And the squid, make a quick drawing, moves forward. But the momentums are the same. This momentum, P of the fluid, is going to equal the P of the squid body, which is the B, momentum of the body of the squid, with the only difference being that they're going to be negatives of each other. One is going to be positive, one's going to be negative in the end. Why? Because when we added all the momentum at the beginning, the P of the squid, we got equal to zero. And so that has to be the momentum at the end. So P of F plus P of B has to also equal zero, which implies that P of F equals negative P of B. Because if those momentums are equal and opposite each other, when you add them together, they will give you zero. Well, if the fluid weighs a lot less than the squid, right? If the fluid weighs less, so its mass is smaller than the mass of the squid, which is bigger, then can we tell which one's going faster? Well, of course, this one's going to have a bigger v if these two things are going to be equal, right? The squid is going to get the smaller velocity, and the fluid is going to get the faster velocity. And that is often the case with propulsion systems. It's the same with air going out of a jet. The air going out the back of a jet is much lighter than the jet itself, so it has to go out at a much faster speed in order to change the momentum significantly of the jet. And that is our first application of the conservation of momentum. So, how do we do a problem like this? We have this example of the archer. The archer has a mass. He and his bow all have a mass to them. So here's our archer. This is example, whatever it is, I don't know. Looks like example 6.3, right, the archer. So you got the man has mass of the man. The bow has mass. You could add in the mass of the bow and the mass of the arrow, for example. And all of those are going to be the total mass of the hunter, right? And so his total momentum at the beginning, since he's not moving anywhere when he shoots the bow, is zero, right? Equals his total momentum. And his total mass is equal to these three things, right? But when he shoots the arrow, this arrow, the mass of the arrow, is no longer going to be part of it. So at the end of the problem, the mass of the hunter, I don't remember what I called him anyway, mass of the hunter plus the mass of the bow are going to be the total mass of the hunter. But then we're also going to have a mass of the arrow flying off in the other direction. Now this hunter is going to be on ice, so when he shoots the arrow forward, he's actually going to go backwards a little bit. And so we're going to have a final velocity that's going to be some value, velocity final for the bow hunter. And the final momentum of the hunter, F of the hunter, is going to equal the total mass of the hunter plus the bow times the velocity final of the hunter, which is going to be a small velocity. Why? Because it's a big hunter, right? If the hunter was the size of an arrow, we would have a much faster moving hunter. But the mass of the arrow, whatever it equals, is going to give us the opportunity to calculate the final momentum of the arrow, which is going to equal mass of the arrow times the velocity of the arrow, right? No, not plus, 3 times. Well, we can start to use these equations now to figure out things. For example, if we don't know the velocity of the arrow after we shoot it, but we do know how fast the hunter is moving backwards, then this final momentum plus this final momentum have to equal 0 when they're added together, because the total hunter velocity at the beginning was 0, so his total momentum was 0. So in the end, you get this equation. You get 0 equals the initial momentum. Final momentum of arrow the 0 has to equal the final momentum of arrow plus the final momentum, sorry, it's a plus, not an equal sign, plus the final momentum of the hunter. So in other words, these two have to be opposite but equal again. Right? So let's take a look at the homework and see if we can't make some sense out of that. Goodness, it's warm in here. What happened to our air conditioning? So homework 6 point... Where's my homework now? Okay, 6.2. Number 1, we have a high-speed stroboscopic photograph. So with stroboscopic photographs, what they do is they do some fast movement in a dark room, and they have a camera that is just open. It doesn't have its shutter closed at all, and they use a strobe light to light up the experiment, so that every time the strobe light flashes, you get an image on the camera of what's happening. It used to be a very common way of taking high-speed photographs before digital photography could start taking them much faster without using this technique. But anyway, it was a very common technique. Still, people do it. So you have a 280-gram golf club, and it's traveling at 60 meters per second. Well, already they've told us the mass of the object and the speed of the object, or the velocity of the object, so now you can calculate its momentum. Make sure that your mass is in kilograms and that your speed is in meters per second. In this case, our mass is in grams, so we need to convert that. It would be 2.280 kilograms for the golf club. And then it's going to strike a 45-gram golf ball at rest on a tee. So all the momentum is carried in the golf club before the problem, and after the problem, the ball is going to go flying off in some direction, and the club will have some follow through, so both of them will be moving after the club hits the ball. So after the impact, or after the collision, we have two objects carrying our momentum. So we're going to have an equation that we're going to deal with. What is the equation going to be? Well, let's take a look at what that equation is going to be. It's always the same equation for conservation momentum. Momentum initial equals momentum final. But these are total quantities. The total momentum at the beginning equals the total momentum at the end. Well, what is our momentum at the beginning? Well, we have the momentum of the club, so we'll call that P of C, and we have the momentum of the ball, P of B. And let's say that the club is moving to the right, and we'll call that positive velocity. So the momentum of the club would be the mass of the club, times the velocity of the club, and the momentum of the ball would be the mass of the ball times the velocity of the ball. And this is all initial stuff, because in the end we're going to take the momentum of the club final momentum of the club plus the final momentum of the ball. Add them together and those should be equal. Well, we already know the mass of the club is 0.280 kilograms. We know the velocity of the club is 60 meters per second. We also know that the mass of the ball is 0.048 kilograms, but we also know the velocity of the ball is 0, so we're just going to multiply this by 0. So this part goes to 0. And that's going to be equal to the final momentum of the ball and the club. Now they've told us the final speed of the club is 44 meters per second. So the final momentum of the golf club is the 0.280 0.280 kilograms, times the final speed, which is the 44 meters per second. And we're going to add that to the final momentum of the ball, which is going to be 0.045. And how fast they say the ball is going. They don't say that's what we want to find out, the velocity final of the ball. So we have this big old equation with all this stuff in it, but in the end it's not that much. We have on the left-hand side one thing that stays, 0.28 kilograms times the velocity of 60 meters per second. And on the right-hand side of the equation, we have 0.28 times 44 meters per second. And we add to that 0.045 times the velocity final of the ball. We're going to put all this stuff on the other side of the equation using algebraic methods and tools and all that stuff, and you solve for the final velocity of the ball. Now, does that make sense? Where we're going with that? Any questions on that first problem in the homework? Okay. Now, the second problem is very similar to it. Instead of a golf club hitting a ball, though, we have a rifle shooting a bullet. Now, the rifle is just kind of looks like that, right? We have a rifle, and the rifle has some particular mass, but the person holding the rifle also has some mass, right? So they tell us that the mass of the rifle is 25 newtons, and then they tell us the mass of the man holding the rifle later on is 700 newtons. Well, these aren't really masses, are they? If it's in newtons, what are these really? This is weight of the rifle, weight of the man. They don't actually say it's a mass in the problem. They do say weight, but it's very easy to mix up mass and weight in this class. So if they give you newtons, you need to convert it back to kilograms. How do you convert weight back to kilograms? Well, weight is equal to weight is equal to mass times gravity, right? So we divide both sides by gravity to get mass. So if we divide 25 newtons by 9.8, you will get the weight in kilograms. And if you divide 700 by 9.8, you will get the weight of the man in kilograms. So that will convert everything back to kilograms, and then it's the same thing. In part A, we're going to, whatever we get our mass for the 25 kilograms, it's going to be about 2.5 kilograms for the mass of the rifle. So that's the mass of the rifle. And the mass of the bullet, they already tell us the mass of the bullet is 5.5 grams, which is 0.0055 kilograms. That's the mass of the bullet. And at the beginning, the bullet and the gun are not going anywhere. So the momentum initially, since it's not going anywhere, is equal to 0, right? In the end, the rifle is going to be going, so this is the momentum of the final of the rifle. That's going to be going backwards. The gun pushes backwards when it goes, so this is going to be a negative direction. And then the momentum of the bullet will be in the positive direction, but those two are going to end up having to be equal. And so in the end we have 0, which is the initial momentums, has to equal the momentum of the rifle, and we know that's going to be a negative number, plus the momentum of the man, which we know will be the bullet, which we know will be a positive number because it's going the other direction, going positive. To the right, if we were thinking of shooting the gun to the right. And all we need to do is put some stuff in here. So what is the momentum of the man? The momentum of the rifle, it's going to be the mass of the rifle, which we decided was about 2.5 kilograms, times the velocity of the rifle, the recoil speed, which is the thing we're looking for. You don't know what it is. It's velocity of the recoil, velocity of the rifle. And then we add to that the momentum of the bullet, which is going to be the mass of the bullet, which is 0.0055, that's 5.5 grams, times the velocity of the bullet, and the velocity of the bullet is 210 meters per second. You say, wait a second, this should end up being a negative number. Well, it is a negative number because we're going to find out that V sub r is negative when we calculate this. I just put that there so I remember which way it should end up going, so I don't get to the end and put the wrong sign on it. But if you've solved this equation for V sub r, you will find that V sub r is equal to some number that it will turn out negative when you do the algebra. And then in the second part, in part B, you're going to do the same exact thing, except in the end, you're not just going to have the momentum of the rifle and the bullet, you're also going to have the momentum of the man, and he will be moving backwards at the same recoil speed as the rifle will, because the rifle pushes on the man and they become kind of one. So your equation ends up looking like this. The zero momentum that you start with when the gun's not moving and the bullet's not moving has to equal the momentum of the rifle plus the momentum of the man plus the momentum of the bullet, and then you solve that equation. Okay. How's that sound? Any questions for number 2? You guys are kind of quiet. Does that mean you're working madly away to finish this homework? Okay. Problem 3 is, again, very similar. You have a girl on a plank. The girl has mass, the plank has mass. They're both originally at rest, so the total momentum at the beginning is 0. And then the girl begins to walk along the plank at a constant velocity in one direction, which means the plank is going to have to move in the other direction, right? And since the plank is so much smaller than the person, that you would think that the velocity of the plank would have to be much bigger for those momentums to be equal, right? But you just have a velocity of the girl in one direction, the velocity of the plank in the other direction, and they have to add up to be 0. Remember that direction matters for signs. So the velocity, if the plank is moving to the left, it's got a negative velocity. If the girl's moving to the right, then she's got a positive velocity, and vice versa. And you just set those two momentums equal to each other. And it's the same thing in number 4. You have a man in a fishing boat, and he throws a ball one way, or a package one way, and that package has a mass and a velocity going one way, which means the boat is going to go the other way, right? This is something we have experience with all the time. We see this all the time in real life. We don't always pay attention to it, but we do see it. Any more questions about homework 6.2? Okay, I'm going to leave you guys to that. Did you have questions about 6.5, or have you not looked at it yet? Okay. Oh, 6.4, right. I forgot about 6.4. 6.4, I believe, is the first thing about collisions. Yep. So let's take a little bit of a break right now, because I'm going to have to go through and do another lecture real quick to fix that one, to get you that one ready to go. Let's take a quick break. I'm going to go get a drink, and we'll meet back here in 5 minutes or so. although I have had one really. right. Let's see what we can finish up here. In section 6.3 and 6.4, we're going to cover collisions in more specific ways. The first thing they're going to start with is what they call, so we've already talked about the elastic collision, we're actually going to talk about the inelastic collision here, because the equation is actually a little simpler. Even though we've already kind of dealt with, we've kind of looked at least, anyway, some elastic collisions. So what is an inelastic collision? An inelastic collision is, we got some feedback going on there. There we go. Okay. So anyway, an inelastic collision is any collision where kinetic energy is not conserved. The momentum will still be conserved, but the kinetic energy will be dissipated somehow. It will be turned into some other kind of energy. And then there's another type of inelastic collision, which they call a perfectly inelastic collision. And that's really quite simple. If you have two objects that are colliding with each other and they stick together during the collision and become one object that's all stuck together, then it's called a perfectly inelastic collision. And there are many collisions that fit this bill. If you have two balls of clay, for example, and you throw them at each other and they stick together when they're done, and there's all one piece of clay, then that's a perfectly inelastic collision. Also, if you have two cars that smash together at an intersection, and they get all bent up together and they stick together and drag each other down the road a little bit, that's also a perfectly inelastic collision. And in these cases, we're going to assume that only the momentum is conserved and kinetic energy is not conserved, of course, because they're crushing and bending and making noise and friction and heat and everything else, and energy is going to be lost there. But momentum will be conserved, and the only thing we really have to think about is that the momentum is in two different objects at the beginning, because they're two different masses, and at the end, after they're stuck together, it's in one mass, which is the sum of the two masses to begin with. And so that's really all we have to think about. In an elastic collision, we assume a perfectly elastic balance with no loss of energy, of course. And of course, kinetic energy and momentum are both conserved. So, what's going to happen mathematically in an inelastic collision, where things stick together and kinetic energy is not conserved, but momentum is? Well, let's take a look at an equation here. Let me get my screen on my ebook. Wow. What just happened to my screen? That's weird. Hold on a second. My screen did the funky. Hold on, I gotta find a proper tool, which I believe is a remote control somewhere. Not there. Where is it? Here it is. Let's see if this works. No. This dumb thing. There we go. Okay. So here's the equation that we're interested in. Essentially we have momentum before two objects. Mass 1, velocity 1, momentum of object 1. Mass 2, velocity 2, original momentum of mass 2. And so they're separate momentums to begin with. It doesn't matter which direction they're going, their velocity, this is in one dimension, so we're not worrying about the vector quantity, but the signs will matter because if this velocity 1 is negative, that means it's moving to the left, and this velocity 2 is positive, it means it's moving to the right, or vice versa. Whatever, they can both be going the same direction, but go in different directions. One can be stopped and have no momentum to begin with. But they have separate momentums at the beginning because they're calculated separately, they're separate masses and everything else. In the end, they are smashed together and they become one mass, and that one mass is equal to mass 1 plus mass 2. And so we add the masses together first, and then we multiply it by one single final velocity, which is the velocity they share because they're stuck together. And if you want to solve for that final velocity, it's really quite simple. You just divide both sides by m1 plus m2, and you get m1 v1, or momentum 1, plus momentum 2 divided by the total mass of both objects together. It will also work for three objects. And you get a final velocity of Vf equals the sum of the momentums over the sum of the masses. That is a perfectly inelastic collision. So in example 6.4, they do exactly this. They have two cars, well, a car and a truck rather, moving towards each other. The truck is much heavier, twice as heavy I think as the car. They smash into each other and they stick together, and so they use that equation and they solve for the final velocity, and they find out that after the collision, the truck ends up pushing the car backwards, and the car undergoes a change in velocity from going forward at 15 meters per second to going backward at forward at negative 15 meters per second and backwards at 5 meters per second, because the truck is so much heavier. They're actually going the same speed at the beginning, but they have different momentums because the truck is twice as heavy. And so in the end, the truck ends up winning in the collision, ends up pushing the car down the road. And there we go. Then they also find the change in kinetic energy of the system. They calculate the kinetic energy at the beginning, which is 3.04 times 10 to the 5th joules. And they calculate the kinetic energy at the end, which is 3.38 times 10 to the 4th joules. It's a 90% loss in energy, it turns out. The kinetic energy is certainly not conserved. It's 90% less than when it started almost. So, pretty significant change in kinetic energy to show that kinetic energy is not conserved. Here they do another problem that's a very classic problem, where they shoot a bullet into a block of wood. So here's the block of wood down here. You put that in a place where you can see it. So here's the block of wood, and they shoot a bullet at it, and this bullet has some velocity 1I, and the mass of the bullet is mass 1. You multiply those mass and that velocity together, you get a momentum, and an initial momentum, and then the bullet hits the block and sticks in it, so that you get a block and a bullet stuck together, mass 1 plus mass 2. Well, the block and the bullet swing up to a certain height, so it changes its potential energy by going up a height h. Well, you can calculate that change in potential energy, just m, which is m1 plus m2, times g times h, and you get that potential energy change. And then that has to equal the kinetic energy when the block and bullet are just swinging upward at the bottom. And so you can use that potential energy to calculate the kinetic energy, and you can use the kinetic energy to calculate the velocity of the block plus the bullet, and then you can use the mass of the block plus the bullet times the velocity of the block plus the bullet to find the initial momentum of the bullet. So you're kind of working backwards, and this is exactly how they do it. They start with kinetic energy plus potential energy after collision and before collision. After collision and at the top of its motion. Then they calculate from that the speed of the bullet, bullet plus the block rather. Then they calculate, they use that bullet plus the block speed to use in the conservation of momentum equation. So what is the key to this kind of a problem? The key is to realize that once the bullet has hit the block and it's stuck together in the block, that the energy will be conserved because the block is just going to swing from a low height to an upper height. And that conservation of energy while the block is just swinging and there's no collision going on allows you to calculate that initial velocity of the block and the bullet after the bullet has hit the block. Then, once you've found that initial velocity, that will be the final velocity for the first part, and you calculate the initial velocity of the bullet so that you have conservation of momentum when you have the collision of the block and the bullet. Sounds kind of confusing, but they walk through it fairly well here. One part of the problem is a conservation of energy problem. The other part of the problem is a conservation of momentum problem. And that takes us on to elastic collisions. Now in elastic collisions, nothing sticks together. Momentum is still conserved, but also kinetic energy is conserved. So we end up having two equations that we can work with if we need them. This first equation is conservation of momentum for each object before the collision and each object after the collision on the right. And then the kinetic energy of each object before the collision and the kinetic energy after each collision. What is the advantage of this? Well, usually the advantage is that you have enough equations to solve the system. So let's go ahead and see what happens. Well, the first thing that they do on this page, on page 179 and 180, is they show you what happens if the masses, if the two balls or two objects have the same mass to them. If they have the same mass, then let's see if that's correct, if I'm remembering what they're doing here correctly. So if both of the balls have the same mass, then you can divide out the mass of everything and you get this equation at the end, which essentially is going to give you the difference of the initial velocities has to equal negative the difference of the final velocities. And so for objects that are the same mass, you can simplify it down quite a bit. And let's see what happens. They use that exact equation when you're playing pool, because all the balls on the pool table have the same mass, and when the balls hit each other, they don't bend, they don't break, they don't crush together and become one ball. They bounce off each other pretty elastically. So we're going to use elastic collision. We're going to use this equation where all the mass is the same. We're able to solve for velocities alone without masses. And it's just a conservation of momentum equation that they're using there. However, you could also use conservation of energy in that problem. You want to start with conservation of momentums because it's an easier equation to deal with. But here we come to another problem where there's different kinds of energy and conservation of energy. So there's spring potential energy, and there's kinetic energy, and there's conservation momentum. And if you go down here and look here, they're using conservation of momentum at the beginning, and they calculate the final velocity of block 2 using conservation of momentum. And then they use the energy equations to calculate how far the spring will compress. Initial energy has to equal final energy. They use kinetic energies initially, kinetic energies finally, but they also have a spring potential energy added on the end because the spring gets compressed. So you can use conservation of energy as long as those energies are not lost in breaking, bending, scrunching, stuff like that of things together. Now, in the homework, what that looks like is homework number 6 point, whatever this is. I don't know what this is. It's some assignment I was giving you at some point. But anyway, this is the homework that shows this. So we have an archer shooting an arrow, shooting the arrow towards a 300-gram target that is sliding in her direction at a speed of 2.25 meters per second. So the arrow has a mass, the target has a mass and it has its velocity, so it has an initial momentum. The arrow has a mass, has a velocity, it also has an initial momentum. Final momentum says what is the speed of the arrow after passing through the target. So the arrow actually passes through the target, right? And then they also tell us the final velocity of the target. The target's stopped by the impact, right? The target gets stopped, and so we know the final velocity of the target. We just don't know the final velocity of the arrow. Well, we know the initial momentum of the arrow, the initial momentum of the target. Add those two together and you get your total initial momentum. And that has to be equal to the final momentum, which is the momentum of the arrow, which is still moving, but we don't know that velocity, so we're going to just write that as a variable. And the momentum, final momentum of the target, which is 0 because it's stopped. So in other words, the arrow has to be carrying the same amount of momentum as the entire system did at the beginning. That's all there is to it. Problem 2 is also a conservation of momentum only equation because it is a it's a perfectly inelastic collision. Part 3 is a perfectly inelastic collision, but it's the ballistic pendulum. So you have to realize that when it changes height, it conserves its energy during the swing, but it doesn't conserve its energy as the bullet hits the block. And then question 4 is actually the first delving into what we call glancing collisions, where energy is conserved in momentum is conserved in more than one dimension, and kinetic energy is conserved because it's a perfectly elastic collision. Number 5 is another problem where we're going to have a part of the problem where momentum will be conserved when the bullet hits the block, but we will also have a part of the problem where energy is conserved as the block falls downward towards the ground. Because just dropping something is very conservative of energy. The only thing that takes energy away from it is the air friction and friction in the air, and that's not very much. It's very small. So we're good to go there. Oh, I gave you 6 questions on this one. Man, that's not nice. Elastic equation on the first one. We have 2 objects with masses and velocities. You should be able to figure out that. It's just mass times velocity of the first object plus mass times velocity of the second object at the beginning, both of those, equals their momentums at the end. Mass times velocity of first object and mass times velocity of the second object at the end. For all the things like mass and velocity that you don't have numbers for, you put in a variable, and that's the thing you solve for usually, not always, but usually. So the basic idea of those 2 homework assignments, 6.2 and 6.4, are that momentum is always conserved. The initial momentum of all the objects added together has to equal the final momentum of all the objects added together. And oftentimes you can use that fact to solve for something you don't know. However, there is a warning, and that is when you have 2 things that are separate to begin with, and when they get stuck together, then they have to be treated as a single object after they've been stuck together in order for the conservation of momentum to happen. And then the elastic collisions. Elastic collisions being when you have 2 objects that bounce off each other almost perfectly without a loss of energy, no deformation, no crazy stuff going on. And you have conservation of momentum, of course, but it's momentum of the separate objects before and the separate objects after. And you have conservation of kinetic energy of the separate objects before and kinetic energy of the separate objects after. Any questions? Anything you need me to clear up on that stuff? Did I do enough homework problems to get you started on those? You guys need me to do any more homework problems to help you out with that? Okay, which one? Excuse me. Okay? Which number is this? Oh, let me see here really quick. Girl of mass MG standing on a place. So part A, for the first part, what did you guys get? So VGP. Okay, VGP is definitely part of the answer, but that's just a velocity. And, well, it's actually that VGP is the velocity of the girl relative to the Planck, right? And so velocity of the Planck relative to the ice is not going to be quite that. It's going to be a ratio, or it's going to be a linear relationship to that that's going to involve the masses. And so what you need to do in this particular case is you need to go back to equation, you need to plug in all the masses in this problem and all the velocities in this problem back into the equation on page, let's see if I can find the equation. Hold on a second. This would be 180, I believe. Plug all those things into the equation on 180 for the velocity of two objects, this equation 6.14, and then solve for the velocity that you want to solve for. Does that make sense? So in problem 3, you have two objects with two different masses and two different velocities, right? Initial velocities, final velocities, and they have their own masses, right? What you need to do is plug those into that equation 6.14 and solve for velocity pi. Do the same thing for part B, except in part B, you're solving for a different one, right? Any other questions? Okay. Well, that's taken us quite a while to get through that. And since we haven't, I'm assuming you're going to want help with section 6.5 as well. Would that be a safe assumption? Okay, let's go ahead and look at 6.5 today. We'll get as far as we can in 6.5. Actually 6.4 and 6.5. We didn't get quite to 6.4. So let's take a look at 6.4 and 6.5. And go ahead and look at the videos that are on YouTube as well, because those will help you with those sections. I'm going to also extend the homework a little bit extra so that you have some extra time. Let's see what we've got on the homework again really quick. 6.4, 6.2 today, 6.5. So I have all this. Do you guys have time to finish all these assignments today, or you're going to need a little extra time, you think? How's your schedule looking today? Okay. Well, what I'll do is I'll leave them for now, and you guys can work on them. If you absolutely need some extra time to crank some out, I'll give it as needed. We'll leave them out as they are for now, though. So let's take a look at 6.4, 6.5, and then we'll just have to leave 7.1 till tomorrow. We don't want to get too far behind, but I think that we actually changed our schedule a little bit. So let's take a look at our schedule and make sure that we know what we're doing here. We have a... What am I looking for? Okay. Okay. Let's take a look at the syllabus, because I think that I maybe have changed these things somewhere. I'm just not sure where. Oh, goodness gracious. Because my password has been locked out. Oh, I guess not. Okay, we got there. We're good. Maybe. There we go. Okay, so physics, itinerant, syllabus. Okay, so 6.1, 6.6 Wednesday, 6.2 through 4. Okay, so today we were supposed to get started on 7.1 according to this calendar, and the exam was going to be due by Monday, which we pushed to Tuesday, and we were supposed to be done with everything in chapter 7 this week. Take a look at that, see how we're doing. 7 is going to be done this week. Nope, it's going to be pushed. 7.5 and 7.8 will be so 7. What? 7.5, 7.6 will be due on the 8th. Okay. So we're supposed to be done with all this stuff this week for chapter 7, but it's not going to be due until Monday. So we're pushing that off. And then we'll have to figure this out. I'll have to figure this out later. Let's see. I guess it's good that we got ahead a little bit, because now we're kind of all right. Well, we'll just push on. We'll push on. Today we were supposed to cover, since today is Monday the 1st, we were supposed to cover all the way through 6.5 and maybe get to 7.1. I think we can finish 6.4 and 6.5 here before we're done, but we'll be a little bit behind. We'll try to catch up again next time. So 6.4, moving on. Glancing collisions, and this is where it gets a little bit more complicated, because now we're going to talk about momentum in 2 dimensions. And again, these I do have video of lectures for these on YouTube, so go watch them as well. I go through them in fairly good detail. But really, all you're really going to do is you're going to have the same equations for conservation of momentum, and we're talking about elastic collisions, so these things don't stick together. Momentum is conserved, but the momentum is going to be more in 1 dimension, so you're going to have to split off the momentum by splitting up the velocities into components. So if you notice here in these equations, we now have two equations for momentum. One in the x direction that has the x velocity components, so mass 1 times velocity 1 in the x direction initially, plus mass 2 times velocity 2 in the x direction initially, has to equal mass 1 times velocity 1 in the x direction finally, plus mass 2 times velocity 2 in the x direction finally. You do the same thing in the y direction. And this takes care of momentum and conservation of momentum in the x direction and conservation of momentum in the y direction. However, you do have to realize that sometimes things are moving in one dimension and not moving in the other dimension. And the perfect example of this is this animation here. In this animation, we're going to start off with this ball moving from left to right, and it's only got momentum in the x direction because it's only moving in the x direction. There is no y momentum. However, after it hits ball 2, there will be some momentum in the y direction because the ball M1 will be moved out this way, ball M2 will shoot down this way, and they will each have some momentum in the y direction. However, their y direction momentums will cancel out in the end. So if we see how this starts, we go here and then they bounce up, and now we've got momentum in both the x and the y direction. And you're going to have to calculate how much velocity does ball 1 have in the x direction, how much velocity does ball 1 have in the y direction, and same thing with ball 2. And then you add those momentums initially and finally in both dimensions to get the final result. So let's jump right into an example here as soon as we can. So here we have a collision at an intersection. One car is moving in the x direction here at the top. One car is moving in the y direction, moving upward from the bottom of the truck. They hit and they end up moving off in the right-hand direction, kind of upward in the right-hand direction. And they're actually going to call this an inelastic collision. They're going to call this a perfectly inelastic collision. The car and the truck will stick together afterwards and become one. Well, that'll help us because it'll make our momentum equation a little easier. We don't have to calculate momentums separately. We'll calculate them together with the masses added together. And what they do here is they calculate the momentum of the car and the velocity by taking the mass of the car times the velocity of the car in the x direction only. They're only caring about the x direction right now. Well, of course, initially the car is only moving in the x direction. So you just take its mass times its velocity in the x direction, you're good to go. Same thing with the truck, except it's only moving in the y direction. Right? So down here they calculate the initial momentum of the truck, and it's all in the y direction. However, the final momentum of the car has an unknown in it. We don't know. It's velocity final times the cosine of theta, because that's the x component of the final velocity. And the same thing goes for, what's going on with my computer? I'm trying to show you something that's not showing anybody anything here. Sorry about that. Okay, here we go. So anyway, here's the original. Let me show you the original picture. You're probably looking at it in your book if you're interested in that, but I'm going the wrong way. Here's the original picture we're talking about where you have a car, they actually call it a car a van, but whatever. You have a car moving in the x direction, a truck or a van moving in the y direction. The initial momentum of the car is to the right or in the x direction. The initial momentum of the truck is upward in the y dimension. So we have an x momentum and a y momentum combined to make a upward and to the right momentum, or an upward to the right velocity of these two things stuck together, right? So this final velocity has an angle of theta with the x-axis, and so the velocity final in the x direction is going to be velocity final of Vf cosine theta, and for the y direction it's going to be Vy sine theta. And that's exactly what you see down here. They calculate the initial momentum of the car, and of course it's all in the x direction, so it's just 25 times the mass. And then the final momentum of the car is the final momentum of the system, actually, of both car and the van in the x direction. It's going to be the mass of the car plus the mass of the van, because they're stuck together in one object, times the velocity final of the car and truck together, times the cosine of theta, which is the x component, right? You do the same thing in the y direction, where the van is the only thing moving in the y direction initially. The car doesn't have any y direction movement, it's only moving to the right or in the x dimension. And we do the final velocity, or the final momentum of the car and the van together, which is mass of car plus mass of van times the final velocity times the sine of theta, because that is the y component. Then they have two equations they essentially have two values for initial momentums, one in the x direction, one in the y direction, and two for final momentums, x direction and y direction. We treat these separately, essentially. The momentum at the beginning has to equal the momentum at the end. So here is the momentum at the beginning, momentum at the end for, let's see here, this is for the y direction, gives us this equation. This is for the x direction, gives us this equation. And you can see that we have two unknowns. We have cosine of theta that's unknown, and we have the velocity final, which is unknown. What they do is they solve each of these for the velocity. They actually solve each of these for the cosine of theta and the sine of theta. Then they put the cosine over the sine in here, or sorry, they put the sine over the cosine, and that gives you 5 over 3.75. And that will give you 1.33, and the tangent of theta, which is the sine over the cosine, has to equal 1.33, and then we take that inverse tangent to get 53.1 degrees for that. Then we can plug that back into any other equation to find out what velocity final is as far as its magnitude. So that is the idea behind glancing collisions. What the whole point of doing two-dimensional collision problems is that you have to split the conservation of momentum problem into two types of into two problems. It has to be split into a problem in the x dimension and a problem in the y dimension. And then you have a conservation of momentum equation in the x dimension and a conservation of momentum equation in the y dimension. Solve them separately, and then you can use them to solve each other. The last one in 6.5 is another type of problem that uses similar stuff, but essentially it's just about rocket propulsion. So kind of like the squid. You start with a gas inside of a container, you poke a hole on one side, you call that the nozzle. The gas is pushing outward in all directions except for where the nozzle is, so it pushes down out of the container, and that causes a change in momentum of the gas outside the container, moving from inside to outside the container. And the container has to move to compensate for that change in momentum so that the momentum is conserved. It's really quite simple. However, when you're doing this kind of a thing, you end up having to do some calculus, and this ends up being the equation that you find for the change in velocity of the container or the rocket. Change in velocity of the rocket is equal to the velocity of the gas, of the exhaust, essentially, times the natural log of the mass initially of the rocket divided by the mass finally of the rocket. There's also an equation that they use for what they call the instantaneous thrust, which is essentially the force that is pushing the rocket. So it's mass times acceleration, but they use momentum in it, and they end up with getting the velocity times the mass divided by time in the end. Another equation that they'll have you use. And here they talk about launching a rocket. You know, they have this rocket that's launched up. They want to know if the friction, gravity, and vector, what's the speed of the rocket at burnout. So you're going to calculate to find the change in velocity. You can use that change in velocity equation, which is the first equation, this one right here, which has the natural log in it. It accounts for the speed of the gases coming out and the change in mass of the rocket as it accelerates upward and uses up those gases. Because every second that a rocket uses gases, it actually gets lighter and gets pushed harder. And that takes us to the end of this. They're doing a little bit of force stuff here at the end that we've dealt with before, so it's not too hard to deal with. We only give you one problem involved in that, I think. So that is all of chapter 6. That takes us to the end of things. So let's take a look at chapter 7 and see if we can see what chapter 7 starts with. Maybe that'll kind of almost catch us up here. You know what, I don't want to do chapter 7 yet, because I think that'll confuse the heck out of us. So let's put chapter 7 off a little bit. So when are you guys planning on taking chapter 1 through 6 exam? Wednesday this week? That's a very good idea, because then you can kind of get it behind you and we can move on with chapter 7. So what I will do is, if you have any final questions tomorrow, make sure you have them ready. And I will start chapter 7 tomorrow and get as far as I can in that. I will continue on with chapter 7 on Wednesday. And then we won't have a lab this week. And we will meet next week on Monday again, and I will come up to Broken Bow next Friday for a lab. Does that sound good? Okay, that's all I've got for you today. If you have any questions, I should be in my office for the next hour or two, and you can call me, email me, and I'll do what I can. I'll post this lecture up on YouTube here in the coming few minutes. It will take a while. Posting long videos on YouTube takes some time, but I will get it up as soon as I can. Any other questions? All right, have a good day.